In this video, we'll do an example where we estimate area using a table of values. So the example says a runner's velocity, which is recorded by a radar gun, t seconds from now is given in the table. So there's two rows. The first row keeps track of t in seconds. So it gives us a few different time values like 2, 5, 8, all the way up until 20. And then the second row keeps track of the velocity at those times. And these are in feet per second. So for example, this column says 5 seconds from now, their velocity is 22 feet per second. So the first thing that I want to comment on is notice that some of these velocities are negative. And velocity is something that has a direction associated with it. So when our velocity is negative, it means that they are running in the opposite direction. So whatever direction they were sort of running in when t was 2 and 5 up until 14, all of those had positive velocity, so that was the positive direction. But then they switched their direction and now they had a velocity going in the opposite direction. Okay, so notationally, remember velocity is, we sometimes write this as v of t. Okay, so in part A, it asks us to use the midpoint rule with the maximum number of rectangles to estimate the area under a graph. So let's begin by drawing a picture. So I'm going to make some axes, y-axis, and this would be my t-axis because my other variable is t here. So t, and maybe the vertical one, I'll call this v of t for velocity. And I'm going to draw tick marks at 2, 5, 8, 11, 14, 17, and 20 on the t-axis. And on the vertical axis, I am going to, it's not going to be to scale, so I'm going to put 20 here. I'm going to put 25 up here, and then I'll put tick marks at 21. Let's go to 22, 23, 24, and let me move the 25 closer. 25. And then I'll have this one be 26. And then in the negative direction, let's say that this is where -5 is. All right. So if I'm going to use the midpoint rule, it looks like at first like I have 6 subintervals. But the issue with using 6 subintervals in the midpoint rule is I would need to know what's going on at the midpoints. Like this midpoint is 3.5. This one would be 6.5. But I don't have information in my table about what's happening at 3.5 or 6.5. So because of that, we can't use 6 rectangles because there's not enough info on the graph. But we can use 3. Because if I use 3, here would be one of the pieces, here would be the second subinterval, and the third subinterval. By the way, now my delta x, that whole length of the subinterval would be 6. Now I have information about what's going on at the midpoint. Like I know the value at 5 in my table. So let's go ahead and plot some points. So when t is 2, my velocity is 20. When t is 5, my velocity is 22. When t is 8, my velocity is 23. When t is 11, my velocity is 26, so it jumps up quite a bit there. And then at 14, it sticks to 26. And then at 17, it drops to -5, so that would be somewhere down here. -5, and then at 20, it's at -4. Okay, so a little bit higher than -5, but still a negative value. Okay, so we have these points. Now we've decided, okay, we're going to use 3 of these midpoint rectangles. Okay, so in the first subinterval, the midpoint is at 5, so I'm going to draw a vertical line until I reach the point on the graph, which is here. Then I draw a horizontal line for the top of my rectangle, which I extend to the ends of my subinterval. Then I draw vertical lines to make my ends of my rectangle. Okay, so if we do the same thing at the next midpoint, which is 11, I draw a vertical line until I hit the curve, which is at this point. Then I draw a horizontal line for the top, and then vertical lines down for the sides. Okay, and the last midpoint is at 17. I draw a vertical line till I hit my curve. This one would go down till I hit the point. Then I draw a horizontal line for, in this case, the bottom of the rectangle. and then I draw the sides, and there I have my 3 rectangles. Okay, so remember my notation for midpoints is I write a capital M. I'm using 3 rectangles, so M3. The base of the first rectangle is 6. Its height I can see is 22. The base of the next rectangle is also 6, and its height is 26. The base of this last rectangle is 6, and its height, I'm going to consider its height to be a negative value, because this is a negative output, is going to be -5. So my areas can be negative here. Okay, so I'm going to factor out this common base, that's 6, and that'll leave me with 22 plus 26 minus 5, and this works out to 258. All right, so now part B of this question asks, well, what does the quantity that we got in part A represent? Include units in our answer. So what we just did was, we did 6 times 22 plus 26 minus 5, and we got that equaled 258. So let's think about units here. For the 6, that's in seconds. And for the 22 and the 26 and the -5, these are all in feet per second, because these were our velocities. So when you multiply those, the seconds here and the seconds there are going to cancel, and we'll just end up with feet. So what we're ending up with is sort of a length. Right? I have this 258, and that's in feet. So let's think about what that could mean here in the context of, well, this person is moving, they're a runner, they're moving, we have these velocities. It turns out that the 200 feet represents the net change in their position. So the change in what was their position initially to the position when the time interval ended. Okay. All right, so I'm going to box this. And then I'm going to state the general result. So in general, when we find the area under a derivative graph over the interval from A to B, and it turns out this is a derivative graph because velocity is the derivative of position, which we usually write as S. So this is S prime of t, it's the derivative of position. So what we're actually estimating is the area under a derivative graph, and it turns out the area under a derivative graph represents the net change in the original function f from t equals a, the starting time, to t equals b, the ending time. So we'll see this more formally in section 5.4, but I think based off of what we know now, we're already ready to be introduced to this. So in terms of our goals for this section, at this point we know how to do goal 1, estimating the area under a curve using Riemann sums with left and right endpoints and midpoints.